Here, if I did, oh yeah, no, this is kappa f, that's right, okay. Whereas if I did kappa f, then I would get this. Okay, I was missing that bar here on top of the whole thing. So for f, for operating first with kappa and then with f on z, you would get this. Operating first with f and then with kappa, you would get this, and these are equal only if fm is real, because the rest has been turned real. Excuse me, the rest has been complex conjugated. Here you get fm zm, right? Because the complex conjugate of a product is the product of complex conjugates. So these two commute if and only if the f's are real, right? And so by the same reasoning, we get the same thing here. That's the easy part. Here the coefficients are real. Okay. Now, to commute with pi over 2, then, well, we'll talk about that in just a moment. The most complicated one is commuting with these translations, which we didn't see before. This is what translation does to Z1, and this is what translation does to Z2. Now, if we were to start off with the term Z1 bar, then this is what we would get. And so too with Z2 bar. So we add here are all the linear terms and all the quadratic terms and all the cubic terms. Now, if we have a cubic term that's Z1 bar Z1, then we put an e to the IP1 here. We put an e to the minus IP1 here. We put an e to the IP1 here, and we get an e to the IP1 in the end, a single one. And that is the same as what we've done to Z1. So this operation is okay. The other ones, you can see, they're not okay. They don't match this at all. If we do Z1 bar Z2, then we put an e to the IP1 here, and e to the minus IP1 here, and e to the IP2 here, and we end up with an e to the IP2 in front of the whole thing. So that matches the Z2. And what that tells us is that a term like this is allowed in the Z2 equation. A term like this is allowed in the Z1 equation. And we look at all the quadratic terms, and none of them end up looking like e to the IP1, e to the IP2 the way they should. Okay, you see this one has e to the minus IP2 Z2 bar, so that's not good. The only ones that match are these cubic terms. And so we know that this term here, Z1 bar Z1, can go into the Z1 equation, and so can Z2 bar Z1. It can go into the Z1 equation. Because if you were to okay, this has the same term, is the equivalent of what I've done before here. That is to say, shall we apply the e to the IP1 to the Z1 and e to the IP2 to the Z2 and then make a polynomial? Or shall we start off by making a polynomial and then apply the e to the IP1? If we do the polynomial and we apply e to the IP1, then we will end up with, and if we apply p with p1, then that's like multiplying by e to the IP1. And the only such operation that we can do is to put together these things, and then it's the same whether we multiply by e to the IP1, the Z1s, and e to the IP2, the Z2s, or whether we merely multiply by e to the IP1 at the end. I mean, we can do more calculations, but it's kind of equivalent to that. You seem a little bit perturbed. I can see it's just that. Usual conflict. I mean, this is, you want to know how it works, you want to know that you can do it, but this is long and boring. Right? So what to do? Let me try and do one. We're looking for terms for which this works. So let us look for a term like, let's see about a term like Z1, Z2 bar. Let's look what it does. Okay. So if we apply P1 to this, then, PP1 to the Z1, Z2 first, this will turn this into e to the I P1 Z1 and won't do anything to the Z2. Okay, right, that's the day. Okay. Now we have new terms and we put them together in this way. So we take this one, e to the I P1 Z1, and we have this and this one, we multiply, we get Z2. Okay, so what we've done here is we've first done the symmetry operation, the shifting, and then we've formed our term. Okay? Okay, so that's process one. Now let's do it the other way around. Let us first form our term, Z1, Z2 bar. We have it. Now we want to do the symmetry operation. Okay, we want to do PP1 to it. Excuse me, no, I shouldn't do, I'm doing this wrong. We want to consider how this works in the first equation, say. Okay, so we have this, and now we're going to, yeah, now we're going to, no, this is not, just a second, sorry. We did this to this, and then we did this. Now, we want to see how this goes into the first equation. So we do this, then we apply PP1 to this, and no operation to the second one, and what we get is e to the I P1 Z1 Z2, this product. And, I'm sorry, hold on just a second. Yeah, this is not what I meant to do. This here, I meant to multiply. I meant to multiply this. That's right. Okay. So this seems to work. So what did I do wrong? I said Z1, Z2 bar doesn't work. What did I say happened to it? I guess the idea is that this one works for a P1, but not for a P2. Not for a P2. This one would be okay, because then if I put a P2 here, then I will get e to the IP2 Z2 here, and now I'm going to multiply this by the complex conjugate of that. So I'm going to have e to the minus IP2 Z2. Okay, and now here for this one, I'm going to take this and I will do P1, P2 to it, so that I will have e to the IP1 Z2 bar. And what am I doing to the second one? That's what I'm not too sure of. My basic point is that this thing is not the same thing as that, but I'm not doing a good job. Let me do it. You're around tomorrow morning?
Yeah.
Okay.
Yeah.
Let me do a better job tomorrow. Let me do a better job.
I think I kind of see what you mean.
Yeah, me too, I kind of see. But I'd like it to be a little better than that. I'd like it to be better than kind of see. I'd like to be able to... it's possible it's better in the notes, the detailed notes, but maybe not. I'm not sure. Okay, so accepting that, leaving that aside, we end up saying that the only thing that are allowed are these terms, meaning, and again, it's not just allowed, and I think this is the problem I'm having, is that it's a two vector. I'm allowing terms in Z1 and in Z2, and I'm not taking that into account properly. I don't know quite what I'm doing there with the second vector. So what's allowed in the first term is the ones that end up looking like e to the IP, multiplication by e to the IP1, because that is what you do to the first term here, e to the IP1. So the ones that are allowed in the first term are this one, and this one, and this one. So we have a linear one, we have a Z1 bar, Z1, that's this one, and we have a Z2 bar, Z1, that one we allow, and we allow, for the Z2 equation, we allow just plain a Z2, yes, and we allow a Z1 bar, Z2, and a Z2 bar, Z2. Okay. And the other ones are not allowed, and I'll do that properly for tomorrow. Now, if we look at these equations, we remember them from the third one, the symmetry class. That is to say, we can go back and, here it is. Yes, we had just these. That is to say, we had four complex coefficients, and this first equation involved all multiples of z plus. Sometimes there was z plus squared, sometimes z minus squared, and sometimes just a constant. And the second equation involved all multiples of z minus, sometimes with z plus squared, sometimes with z minus squared, and sometimes just a constant. Okay? And that is the same situation we have here. We have cubic equations. Everything gets z1. Sometimes it's z1 squared that multiplies it, sometimes z2 squared multiplies it, and sometimes it's a constant. Okay, so these are the same equations as before, and the results are the same as before. That is, when we go back, we see that what results did we get from this? We learned that there was the origin, there were the left traveling waves, the right traveling waves, and the standing waves, and and the stability all looked like it all was controlled by the nonlinear coefficients, the cubic coefficients. They, depending on what their relative size were, you had either standing waves, traveling waves, both bifurcating to in the same direction with the standing wave stable, or else the same with the traveling wave stable, or you had them going in the left direction, or you could have them going in opposite directions. So if that's all the solutions to those equations, it's the same for these solutions, except that we're no longer talking about left and right traveling waves anymore. We're talking about this horizontal axis and the vertical axis. So that means we can have solutions to these equations that are all waves like this, solutions that are all waves like this, or solutions that are in equal superposition. And those are the only ones allowed by the symmetry. That's why we don't have every possible wave number combination, the whole circle's worth. We have to have only those. So the same equations of Hopf bifurcation or O2 symmetry, we get, instead of having left and right traveling waves, we now have rolls in the x1 and x2 direction. And we can do the same, okay, the same picture is being reproduced. And you can use the same formulas for the solutions. The solutions are here with they depend on these coefficients that are here, A and B. Okay? So we have just the same. So we see that when in a situation with square symmetry, we have three possibilities for rolls. We have stripes this way, stripes that way, or a superposition. The superposition, of course, are squares, and you're tempted to draw a superposition of this with this as being, of course, this, right? If you add the reds and the blues, you'd think you'd get this. But in fact, you can easily convince yourself with trigonometry that that's not so, that the result of the red plus the blue gives you something that is at 45 degrees. And here's the trigonometry that will convince you. We just take our real expression for u, with our e to the ix1 and complex conjugate, our e to the ix2 and complex conjugate, okay? And we can write these as cosines, right? Where, excuse me, we know that all of these have the same, we know that for the squares z1 and z2 are the same. They have the same amplitude. So we call that r of t, and we take the phase to be 0. And that we can do. So this is cosine of x1 plus cosine of x2, and we know from trigonometry that this is equal to the product of the sum of the cosines and the difference of the cosines. Hence, the lines on which this is 0, this sum, is the lines where x1 plus x2 over 2 is pi over 2. Or the lines where x1 minus x2 over 2 are pi over 2 and 2 pi, what's that? Right, they're x1 plus x2 over 2 is equal, over 2 is equal to pi over 2 plus, that's what's written here. The diagonals with slope plus and minus 1. Okay, so that's a funny thing, isn't it? When you thought that the sum of those was that, but instead it's that. Now, we can find some, but not all of these results in a container with square symmetry, not an infinite square lattice, but with square symmetry, so no more of the P1. We can do an analysis that resembles this. We don't have any phase choice. We can have an eigenvector with 2 rows along x1, or an eigenvector with 2 rows along x2, and it turns out that, excuse me, this leads to 4 equivalent branches, those with rows along x1, those with rows along x2, and the reflection. Okay. So those are these. Now, again, the power of the nonlinearity. If rolls this way are an eigenvector and rolls this way are an eigenvector, then the combination is an eigenvector. Okay, so you could have, in fact, you could have rolls in any direction. So you ought to be able to have these others. These are all equivalent to one another, and the reason they're equivalent to one another is because you have rotation symmetry. You have rotation by pi over 2. So a diagonal goes to another diagonal, goes to another diagonal, goes to another diagonal. However, symmetry is very strong. Symmetry is not a linear property, it's a nonlinear property. This follows for all the solutions. So too, the rows that were oriented this way and the rows that were oriented this way are necessarily, they're not just eigenvectors at the same threshold. They have all the same properties because rotation by pi over 2 is a property of the system. And hence, if you're in a square now, if you have rows that are oriented this way, then your rows oriented this way had better have all the same properties. But rotation by 45 degrees is not a symmetry property. You can go from a rotation like this to a rotation like this by taking a rotation, but of 45 degrees. And that's not a symmetry of a square. So it turns out, but there are eigenvectors. They're eigenvectors because you can add eigenvectors. That's a linear property only. That's unlike symmetry. That's only a property of linearity. If you have an eigenvector like this and you have an eigenvector like this, you can add them together and get a new eigenvector. But that's superposition. That's a linear property. So you have an eigenvector like this, and that eigenvector is losing stability at the same point, because if this eigenvector and this eigenvector both have 0, if this eigenvector crosses 0, the eigenvalue corresponding to this eigenvector crosses 0, then necessarily this one does too, because it's just a rotated version of it. And necessarily so does any sum of it. Not only the 45-degree one, but any variant of it. They all cross 0 at the same time. So they all bifurcate. But now for the nonlinearity, you're restricted. You're restricted to, as it turns out, to these and to these and to the diagonal ones. And the diagonal ones are not equivalent. Okay. Although these are equivalent to these because they're related by rotation by pi over 2, summing this and this to get this, that's not something that survives nonlinearity because that's a sum. Linear superposition is linear superposition. So it turns out that in a situation with, in a bifurcation diagram in a square, you end up, at every bifurcation, you end up with 8 branches, which are in 2 sets. 4 are equivalent to one another, and the other 4 are equivalent to one another. And that's what here is an actual simulation of Marangoni convection in a square. And what is Marangoni convection? We talked about Rayleigh-Bernard convection. Rayleigh-Bernard convection is caused by the density dependence on temperature, so that if you heat from below, you end up having light fluid here. Marangoni convection is caused also by temperature difference, but it's the surface tension that varies with temperature. And hence, once you have some cold fluid, it is dragged along the fluid by this surface tension. Yes?
Why is four branches and no other number?
I'm sorry, why 4? This argument here. If you have rolls here, here you have a box with 2 rolls. They're doing this. So you have this, or you have this. Okay, that's in this direction. Now in this direction, you also have this or this, and that makes 4. Now in the diagonal direction, you have this, and that makes 2. And then in this diagonal direction, you have this, and that makes 2 more. So 4 like this, 2 like this, 2 like this, 2 like this, and 2 like that. And so here is a bifurcation diagram of bifurcation of a Marangoni convection in a square. Some of the branches aren't drawn, as you can see, since 8 branches bifurcate all at the same time. Here is a branch that results from 2. This is a pitchfork where 8 branches come out at the same time. This is one, once the branch has continued, this 2 branch, the 2 rolls look like this. And then it has, of course, you can imagine it has partner that looks the other way, right, with the solid lines on the bottom and the dashed ones on top. Why not? It's a square, it's sitting here, it doesn't care. So that you know. You also have a third one, which is rotated by pi over 2, where this big fat thing is on the left. And then you have a fourth one that's equivalent, where the big fat thing is on the right. So that's this set of branches, and whatever property is being measured here is the same for all 4. Simultaneously, including stability, because here the solid curve indicates stability. Simultaneously, at this bifurcation, this is what we just said, there are another 4 branches, and here's a representative here of one of them. And you can see, this big fat guy is at the upper left corner. Well, he could have been at the upper right corner, or he could have been at the bottom right corner, or he could have been at the bottom left corner. Right? So there are 4 this is a representative of 4 branches. And of course, this other set of branches, although they appear at the same bifurcation point, they share the same eigenvector, they share the same bifurcation point because because you had 2 eigenvectors, the one in the 1 direction, the one in the 2 direction, so that already made 2, but you also had sums and differences of the 1 plus 2 and 1 minus, and all of those gave rise to bifurcations, but they have the other one has different properties, and you can see this is an unstable branch here, this diagonal branch. Now, this branch is going to continue and is going to eventually disappear. You see this solid. First, he's going to become unstable over here. He's going to have all kinds of adventures, but he's eventually going to disappear. And the same logic holds when he disappears. When he disappears, that's because one of his eigenvalues turns 0. And his eigenvector is going to be oriented a certain way. And all of the other 4 branches will disappear at the same time, but so will these other ones. So you'll have another bifurcation over here, where these branches, all 8 of them disappear, even though this set and this set have had a completely different lifetime. They could have had other bifurcations. This one's been unstable, and this one was stable. Then this one became stable when this one was unstable. They led all kinds of different lives. At the very end, they disappear all at the same time, for the same reason that they appeared all at the same time. So that's a weird and interesting result. Now you see some other illustrations of bifurcation theoretic principles. Look at this branch here. This branch here has, what symmetry does it have?
Rotation, reflection.
It has all the symmetry, it has rotation, it has all the symmetries of a square. This one, there's no broken symmetry here. No broken symmetry, hence it's not a pitchfork. A pitchfork implies that there are, in a pitchfork, there are always several solutions that are related by symmetry. If it's a circle pitchfork, it's the phase. If it's just an up and down pitchfork, it's well left or well right, or this way or this way. This one, it has any symmetry operation you do to it, whether it's rotation by 2 pi over 4 or reflection, gives you the same thing. Hence, necessarily, it arises from a transcritical bifurcation. Merely just looking at the form of it tells you this is a transcritical bifurcation. It's labeled T1. I mean, the diagram is so full of stuff that you can't quite tell that. But this one emerges from T1, necessarily. So there, I guess that's what I wanted to show you. About this diagram, how well it goes along with these symmetry properties. This one too, this is also a transcritical bifurcation. It also has square symmetry. Yes.
Quick question. You said the square one has all the symmetries.
Of the
basically.
square, yes.
Do we not count translation as a symmetry group?
Not now. I mean, indeed, I went to a lot of trouble to do that originally, and that was the problem with where I couldn't answer your question properly and all this. And yet, at this point now, I dropped it, and I'm not talking about a square lattice anymore. I stopped that. That ended here, and now I'm talking about a container with square symmetry. It's not a lattice anymore, and we don't have translation. We have backwards. And perhaps I should have just started with that, and then I wouldn't have gotten into the trouble with the P1 and the P2s. Okay. Yes, here are the eigenvectors. This is. You can see how this one then gives rise to. Equivalent to this eigenvector is the one that's here, and then not equivalent, but also an eigenvector, is the sum of this one with this one. And then you have the ones that don't break any symmetry at all, like this one. And this one here has symmetry, but, okay, of course, there's this one, and then there's the one that's, there's minus it. And
Pi rotation.
I'm thinking, can you do hold on, does this one have, yeah, it has pi rotation, yes. Can you make the same kind of reasoning about this one as this one? I don't think so, no, you can't. If you do a pi over 2 rotation to this, you just get not minus it, so not a different shape.
Okay.
So I don't think that you, this one does not, this one gives rise to that weird phenomenon with the 8 branches. This one does not. Nor does this one. And nor does this one, of course. Okay. So there, I think. That's that. Now let's discuss hexagons. And you remember that thing with that coefficient G1, and now we will understand that. For the hexagons, hexagons can be decomposed into 3 different directions, K1, K2, K3, are along an equilateral. There's 120 degrees between each of them. Or you could say 60 degrees because you must have the complex conjugate too. And we write any real function as a sum of e to the I k1x, e to the I k2 dot x, and e to the I k3 dot x. You recall I said that was why I was preparing before with x1, x2, and x3, plus complex conjugates. Now, and I hope I don't get into trouble again, the 2 pi over 3, this we understand, we rotate the 3 one into another. That turns Z1, Z2, Z3 into Z3, Z1, Z2. Kappa, we are going to complex conjugate each of them. That turns each one into that one. This one turns into that one, and this one turns into that one. And now the translation, okay, we had no trouble with the definition, and I guess I won't get into any trouble if I don't try and do the calculation. But the point here is that there is an operation which is allowed. Let us look at the quadratic function Z2, Z3 complex conjugate. Okay. If we started by doing e to the I k2p